A chemical reaction can be defined simply as the interaction and chemical transformation of the atoms and molecules of usually two or more substances to form a new substance or substances. The substances that take part in a chemical reaction are known as the reactants, while the new substances formed after a chemical reaction has occurred are known as the products. A chemical reaction results in the rearrangement of the atoms and molecules of the reactants to form products with new atomic and molecular orientations. This is achieved through the making or breaking of bonds between the constituting atoms. It is worth noting here that in a chemical reaction, atoms of one element do not change into those of another element. It is also worth noting that atoms do not disappear from the reactant mixture or appear from elsewhere. Chemical reactions are different from the physical changes in that the former leads to the creation of new substances, while the latter merely alters the state of the original substance without changing its chemical composition. A very common everyday example of a chemical change would be the burning of paper. Paper, which is made up mostly of cellulose fibers, when burned, creates a new substance in the form of black ash, also known as carbon, and also releases a gas known as carbon dioxide and water in the form of water vapor. There are many different forms of chemical reactions that take place in nature. These can be categorized into 5 major types, namely combination reaction, decomposition reaction, displacement reaction, double displacement reaction, oxidation and reduction reaction, or simply redox reaction. In this video, we'll be demonstrating a few laboratory examples of the second type of reaction, which is decomposition reaction. Decomposition reaction can simply be defined as a type of chemical reaction in which a single substance or reactant breaks down into 2 or more simpler constituent substances. A typical decomposition reaction can be represented by the chemical equation A gives B plus C, and so on. The breaking down process involved in a decomposition reaction may be catalyzed or sped up by heat, light, electricity, or even a change in pH. In some cases, the chemical breakdown products can recombine instantly in a reversible process to form the reactant again. In this video, we'll be demonstrating a few examples each of chemical decomposition by heat, light, and electricity. To perform these experiments, we'll need the following: ferrous sulfate crystals, test tubes, test tube holder, spirit lamp or Bunsen burner, blue litmus paper, spatulas, lead nitrate, calcium carbonate, mercuric oxide, ammonium chloride, silver chloride, dilute sulfuric acid, plastic droppers, retort stand with finger clamp, an apparatus consisting of a test tube fitted with a one-hole rubber cork and a glass delivery tube bent in 2 places as shown. An apparatus consisting of a test tube fitted with a one-hole rubber cork and a delivery tube bent at right angles in 2 places like so. Small pneumatic trough or a 250 ml beaker, a 500 ml beaker, glass funnel, china dish, absorbent cotton, tripod stand with wire gauge, watch glass, insulated copper wires, and a 6-volt battery unit. Before the start of the experiments, make sure to follow all necessary safety precautions in handling chemicals, fire, and electricity. Wear lab coat, safety goggles, and gloves. Salts of lead, silver, and mercury are generally toxic both by ingestion and skin contact. Oxides of sulfur and nitrogen are toxic irritants and should not be inhaled. Fumes of ammonia and hydrogen chloride are irritants and should not be inhaled. Testing of gases using glowing or burning splint should be done very carefully, preferably under the teacher's supervision. To perform this experiment, take a small amount of dry ferrous sulfate crystals in a test tube. Note that the color of the salt is light green. Now, while holding the test tube safely using a test tube holder, begin heating the bottom of the tube on the flame of a spirit lamp or a Bunsen burner. Continue heating the tube for several minutes. Record your observations. As you heat the green ferrous salt in the tube, it initially turns from its original light green color to a white or pale green. Water vapor is also seen to condense at the upper ends of the test tube. As you continue heating the salt long enough, the white color gradually changes to a brown or reddish-brown color. At this time, you can also see an emission of colorless to faint cloudy white fumes of a gas from the salt in the tube. A slight whiff of the fumes present a characteristic odor of burning sulfur. A strip of moistened blue litmus paper, when placed near the mouth of the test tube, also turns red, indicating that the fumes are acidic in nature. The thermolytic decomposition of ferrous sulfate is elucidated by the chemical equation shown here. Ferrous sulfate usually exists in a hydrated form, specifically in its heptahydrate form. When the green hydrated salt was heated, it began losing all its water of crystallization and changed into its anhydrous form, which is white to pale green in color. As you continue to heat the salt, the reddish-brown to black residue formed at the end is in fact ferric oxide, which is formed by ferrous sulfate losing its water of crystallization and then eventually decomposing to release its breakdown products. The smell of burning sulfur is due to the release of oxides of sulfur, namely sulfur dioxide and sulfur trioxide, both of which are readily soluble in water. They could turn blue litmus red due to their acidic nature. This reaction is categorized as an example of heat-catalyzed decomposition reaction or thermolysis because a single reactant substance is involved, which breaks down into two or more constituent products. A similar thermolytic reaction can be demonstrated using many other chemical compounds, most commonly compounds such as lead nitrate, calcium carbonate, and mercuric oxide. In the case of lead nitrate decomposition, nitrogen dioxide gas is released as a reddish-brown color with a pungent odor. A yellowish residue of lead monoxide is left behind in the test tube. In the case of calcium carbonate decomposition, the end product is a white residue of calcium oxide along with carbon dioxide, which is emitted in the form of a gas. The identity of the gas can be confirmed by passing it into a solution of calcium hydroxide, commonly known as lime water, which then turns milky as it reacts with carbon dioxide gas. In the chemical decomposition of mercuric oxide, when a small amount of the brick red colored compound is heated in a test tube, it gradually turns black and beautiful silver-like droplets of liquid mercury begin to coat the inner walls of the test tube, while oxygen gas is released as the reaction progresses. The released gas can be collected in another tube by downward displacement of water. When a glowing splint is introduced into the gas-filled test tube, the glow intensifies and may even reignite with a brilliant flame, showing that the gas is indeed oxygen. As previously stated, some substances like ammonium chloride also undergo heat-catalyzed decomposition reaction. However, the products formed can immediately recombine, given favorable conditions, to transform back into the original reactant substance. So the reversible decomposition reaction of ammonium chloride can be considered as decomposition reaction coupled with combination reaction. Because of this very property, the interesting thing about the thermal decomposition of ammonium chloride is that it can also be considered as a form of physical change called sublimation, and is in fact a common classroom demonstration for the process of sublimation. Sublimation is a physical process wherein a solid substance directly converts to its gaseous state without going through its liquid phase. It is considered a physical change because it only involves a change in the state of the matter without any alteration in the chemical state of the substance. To perform the reversible decomposition reaction of ammonium chloride, take one spatula full of solid ammonium chloride crystals and place it in a china dish. Cover it with a glass funnel. Plug the stem of the funnel with a small piece of cotton or glass wool. Place this setup on a wire gauge in a tripod stand and heat the ammonium chloride slowly using a spirit lamp or Bunsen burner. Watch closely. After a couple of minutes of heating the ammonium chloride, you will observe copious amounts of white fumes begin to form and occupy the inside of the funnel. The salt also begins to disappear slowly and turn into a gaseous phase. Meanwhile, throughout the inner walls of the funnel, which is comparatively cooler than the porcelain dish which is being heated, thick white deposits can be seen forming. At the end of the reaction, you can see that all the solid ammonium chloride crystals in the china dish had disappeared and are completely deposited as white residue on the inner walls of the funnel and even on the sides of the porcelain dish. The reversible thermolytic decomposition of ammonium chloride is represented by the chemical equation shown here. The gaseous phase formed by heating solid ammonium chloride is actually a mixture of ammonia and hydrogen chloride gas. It is worth noting here that the gas formed is not ammonium chloride in vapor phase. As the mixture of ammonia and hydrogen chloride gases reach the cooler parts of the funnel, they chemically recombine to form solid ammonium chloride again, which is seen as white deposits on the inner walls of the funnel. Chemical decomposition reaction can also be brought about by radiant energy from sunlight or artificial light. A classic example is the light-catalyzed decomposition or photolysis of light-sensitive silver salts such as silver chloride. To perform this experiment, take a small amount of silver chloride in a watch glass and spread it out evenly to form a thin layer. Note that the color of pure silver chloride is white. Now, leave the watch glass in sunlight for several minutes and observe what happens. After exposure to sunlight, the white silver chloride gradually turns dark gray in color. The photolytic decomposition of silver chloride can be represented by the following chemical equation. The grayish residue that remains in the watch glass is elemental silver. The yellowish-green fumes released from the silver salt is chlorine gas. In fact, if you observe the silver chloride closely enough against a white background, you may be able to visualize yellowish-green fumes emanating from the silver chloride. Since a single reactant, in this case silver chloride, decomposes into its constituent products, this reaction is categorized as an example of decomposition reaction. And since light energy is required to bring about the chemical breakdown process, it is known as photolytic decomposition reaction, or simply photolysis. The power of electricity can also cause chemical decomposition reactions. Electrolysis of water is a fine example. To perform this experiment, take the 250 or 500 ml beaker and fill it with clean water almost till the brim. Add several drops of dilute sulfuric acid to the beaker and stir. Fill 2 test tubes to their brims with the same acidified water from the beaker. Cover the mouths of the tubes with your 2 thumbs or fingers and immerse the tubes upside down in the beaker. You can also support the tubes using a sheet of cardboard with 2 holes as shown here. Next, take the 2 insulated copper wires and introduce their exposed ends into the mouths of the 2 test tubes like so. Connect the other ends of the 2 wires to a 6-volt battery unit. Allow the experiment to run for some time while observing the test tubes closely at intervals. When the electrolysis setup is connected to the power supply, you can almost immediately start to notice tiny gas bubbles originating from the exposed ends of the wires. On closer inspection, you'll also notice that the gas bubbles are formed more vigorously and at a faster rate in the wire connected to the negative terminal or cathode of the battery, as compared to the wire connected to the positive terminal or the anode. If you allow the electric current to pass through the wires long enough, you'll also notice that the gas bubbles begin to collect in the upper ends of the 2 test tubes, and that the volume of gas that collects in the cathode tube is seen to be twice the volume that collects in the anode tube, which you can measure using a ruler. Allow both test tubes to be completely filled with the gases. First, remove the tube from the cathode terminal as it fills up first with the gas. Plugging the mouth with your thumb, remove the tube from the beaker and test the gas by introducing a burning splint into the mouth of the tube. You will observe that the gas ignites explosively with a characteristic pop sound. Do the same with the anode tube once it fills up completely with the gas. You will notice that when a glowing splint is introduced into the tube, the glow intensifies and may even reignite with a brilliant flame. The electrolytic decomposition of water follows the chemical equation shown here. The gas collected in the anode tube is oxygen gas released from the decomposition of water. Oxygen, being a supporter of combustion, causes the glowing splint to burn with a bright flame. The gas collected in the cathode tube is hydrogen gas, which explosively ignites, producing the characteristic pop sound when a burning splint is introduced. In this video, we've discussed and demonstrated some common examples of decomposition reactions. You have probably noticed that all these chemical breakdown processes that we have demonstrated required an external source of energy, either in the form of heat, light, or even electricity. Such reactions in which energy is absorbed for the reaction to proceed are known as endothermic reactions. Can you think of any common examples of chemical decomposition reactions that are exothermic, meaning some form of energy, usually in the form of heat, is being released rather than being absorbed? Think of hydrogen peroxide. This oxide of hydrogen, even when stored in a cool and dark place, spontaneously decomposes into its constituents, water and oxygen, and in the process releases heat energy, thus making it exothermic. The process, however, takes place relatively slowly. However, if hydrogen peroxide is mixed with a small amount of an external chemical catalyst, the decomposition reaction takes place instantly, in fact explosively, to produce copious amounts of oxygen and heat. This catalytic decomposition of hydrogen peroxide is the basis for the famous elephant toothpaste experiment that you are probably already familiar with. I've covered in detail about the elephant toothpaste experiment in a separate video, including the science behind the reaction of this interesting and fun experiment. The links are in the description below. So this was all about chemical decomposition reaction and their different subtypes. In separate videos, I've covered the other types of chemical reactions as well. Make sure to check out those videos too. The links are in the description below. If you found this video helpful in your studies or teaching, then please do consider subscribing to my channel and sharing it with friends, colleagues, and anyone for whom this video might be relevant. Thanks for watching.